On February 3rd, 2014, we had our prerequisite quiz for the class, in which the goal was to revisit some of the concepts that were learned in the linear systems class. In this video, I will go over that prerequisite quiz questions and provide solutions, as well as try to explain some of the concepts that I have seen students struggle with in their solutions. So let's start with the first problem in the prerequisite quiz. The problem says that all you are told is you are given a system which is single input, so it takes an input X, it is single output, generates an output Y, and it's a discrete time system, but we don't know anything more than that. What we are then told is that the input and output relationship of this discrete time system are given by this expression. And part A asks, what is the impulse response, which commonly is written as Hn. Now, for a discrete time system, you should remember that the impulse response is simply defined as, regardless of whether the system is linear or time invariant or time varying, the impulse response of a system is always defined as, if I input an impulse, what is the output? Yn. Whatever is the output is called Hn. So to answer this part, all we have to do is replace the input X with the impulse delta. What this means is we replace Xn with delta of n, and we replace x of n minus 1 with delta of n minus 1. So if we do that in the input and output relationship of this system T, what we get is Yn. I'm just writing down the above expression in part A with replacing x by delta. So I get n plus 1 delta of n plus n delta of n minus 1. And this output, since it corresponds to the impulse function, is called the impulse response. Now, to some extent, the mathematically expressed the impulse response of the system part of this part A is solved if you write this. I would, however, like the students simplify this further. I did not deduct marks though from students who did not end up simplifying it any further. So the simplification of this basically stems from the fact that what is n plus 1 delta n, and what is n delta of n minus 1. Okay. So remember that delta of n is just value 1 at n equal to 0, and it's 0 everywhere else. So if I multiply this delta of n with n plus 1, I will get 0 everywhere except at n equal to 0. So n plus 1 at n equal to 0 will be 1. So I'm going to multiply 1 with 1. This 1 is due to n plus 1 factor, and I get back simply delta of n. Okay. So n plus 1 delta of n is nothing but delta of n. Similarly, delta of n minus 1 is 0 everywhere except at n equal to 1, where it is 1. And then, so this is delta of n minus 1, and then we multiply it with little n, which when we multiply that will be 0 everywhere except at n equal to 1. So when we multiply n with delta of n minus 1, we are multiplying 1 times 1, which is 1. So this is nothing but delta of n minus 1. So a simplified form of this yn or hn, you can call it either way, is delta of n plus delta of n minus 1. This is the first part of part A answer. If you got this, then you got it exactly right. If you got this version, then I still gave you all the credit that was due for this up to this region. Now the second part of part A asks to provide a labeled plot. That is easy because what this is saying is you have this corresponds to an impulse at n equal to 0. This corresponds to an impulse at n equal to 1. So all you have is your hn is given by an impulse of height 1 at n equal to 0, an impulse of height 1 at n equal to 1, and 0 everywhere else. Okay? So this is your plot of hn. So this completes our discussion of part A of the first question. The second part asks whether the system described by the relationship y of n equals n plus 1 xn plus nx minus 1, whether this is a linear system or not. Now, the important thing to note here is that linearity has nothing to do with whether this system has an impulse response, because every system in the world is going to have an impulse response. The definition of impulse response is simply if I input impulse, what is the output? That output is called the impulse response. So we have to really check whether the system is linear or not. I'll just write here the relationship so that we can remember that n plus 1 xn plus n of xn minus 1. Now, there are two ways of going about this solution. An easy way of looking at it is, which is sort of a, you can think of it as a cheat code, is that if the system output depends upon the input only as its linear powers. In other ways, the output does not involve any powers of x other than power equal to 1. And the output does not involve some constant shift. Then the system is linear. And so this is indeed true, because if we see, first of all, this output has no constant shift. So it is not that we have, say, plus 7. If it had this, then it won't be linear. It doesn't have that. And it only depends upon the input through linear powers. So the power of input is always 1. So because of this, this is indeed a linear system. If instead of this, I had, for example, a power of 2 here, or maybe a power of 1/2, or any other power on the input, then it would not have been a linear system. You can also check the answer to this question more formally. Remember, the definition of linearity is that if I have input x1n and it produces output y1n, okay, which in this case will produce n plus 1 x1n plus n x1 of n minus 1. I'm simply replacing x by x1. And if I have an output x2n, if I have an input x2n and the output y2n is given by, again, I'll just replace x by x2 plus n x2 of n minus 1. And now if I take a linear combination of these two, so I define some x3n, which is, let's say, alpha of x1n plus some beta of x2n, where x1 and where alpha and beta can be any complex or real valued numbers. We have to now find out what is the output in relation to x3 of n. If the output, let's call that y3 of n, if it ends up being the linear superposition of the respective outputs of x1 and x2, which means if they end up being y1n plus beta y2n, then we will declare that this system is indeed linear. If not, then this system is nonlinear. So we can check that. We simply replace in the input-output expression that is given here, yn equal to n plus 1 xn plus n xn minus 1. Remember, these are just, I did those for example. So I do that, I get y3n equals n plus 1 x3n plus n x3 of n minus 1. And now I input the value of x3n, so I get alpha of n plus 1 x1n plus beta of n plus 1 x2n plus alpha of n x1n minus 1 plus beta of n x1n minus 1. And now I combine the alpha and beta terms together, so I get alpha times n plus 1 x1n plus n times x1 of n minus 1 plus beta times n plus 1 x1 x2 of n plus n times x2 of n minus 1. Now if you notice, this is nothing but y1 of n, and this is nothing but y2 of n. Okay. So what this means is that my y3 of n equals alpha of y1 of n plus beta of y2 of n. So indeed, this system, if you don't want to take this direct route of just checking that there is no additive term which is not a function of input, and the powers of inputs are only given by power of 1. If you don't want to do that, you can formally compute this and show that the principle of superposition holds, which means that if you input x3n, which is alpha x1n plus beta x2n, then the output of this system is linear superposition of the outputs, which is y3n equals alpha y1n plus beta y2n. Both the approaches were acceptable to me in the quiz, and regardless of how one did it, I gave them complete 1 point for that. The third part of this question asked us to say whether T is a time invariant system or not. So I'll again write the input-output relationship because that is all that we have to work with in determining whether this is a time invariant system or not. Now, there are, just like the previous part, there are two ways that you can approach this. One is the more formal way, which relies on the definition of time invariance. So if you remember, the definition of time invariance is that if xn produces an output yn, then what happens when we shift the input? A time invariant system is one in which the output, its nature doesn't change except that it is delayed by the same amount as you delay the input. So does inputting x of, let's say, n minus n naught, where n naught can be any integer, give us y of n minus n naught? So let's do that. Let's ask ourselves what happens if we input x of n minus n naught, which means that we simply replace x by x of n minus n naught. So this means that xn gets replaced by x of n minus n naught, and xn minus 1 gets replaced by x of n minus n naught minus 1. So if we do that, and let's call that output y prime, because we don't know if that output will be y of n minus n naught, so I don't want to call it y of n minus n naught. Let's call it yn prime. We get n plus 1 x of n minus n naught plus n x of n minus n naught minus 1. Now let's compare this to what is y of n minus n naught. So if y of n is this expression, then to make it n minus n naught, we just replace everywhere that there is n, we replace that with n minus n naught. So y of n minus n naught is n minus n naught plus 1 times x of n minus n naught plus n minus n naught times x of n minus n naught minus 1. Now if we compare the two, we see that they are not equal. Although both have x of n minus n naught and x of n minus n naught minus 1, where they differ is that the coefficient next to x of n minus n naught is n plus 1 here, whereas it is n minus n naught plus 1 here. So since if I shift the output, if I shift the input, my output is not shifted by the same amount. My output y prime n is not equal to y of n minus n naught. This means that this is not a time invariant system. Now there is a shortcut for that to check whether it is a time invariant system or not, and the simple shortcut is that if ever your system output expression involves coefficients which are functions of n, so this is the case where your expression involved something which was a function of n, not as part of xn, but just a coefficient. This is the coefficient, it is n plus 1. This is a coefficient, it is n. Because of this, you are bound to get time varying systems. Okay, so you can look at other examples as long as you don't have coefficients which are functions of n, then you get time invariant systems. Otherwise you get time varying systems. Okay, again, this is the problem where regardless of what approach people followed, I gave them full points if they gave the right answer and gave the justification. Otherwise they got only half the point. we now come to the second question of this quiz, which was specifically about a single input, single output discrete system. But now we said that this is an LTI system. And if you remember, an LTI system, all you need to describe an LTI system is its impulse response. So oftentimes, instead of writing the LTI system, we just write the impulse response in the place of the LTI system. And we are given the impulse response, which is delta of n minus 2. Effectively, what this system is doing is it is taking the input and it is delaying by 2 samples. Okay? So part A asks you to tell what the output yn is if the input is xn equal to 2 of delta n plus 1 minus 3 of delta n minus 1. We have to tell what is yn. Now, since this is an LTI system, we know that the input-output relation in LTI systems is given by convolution. So we get xn convolution with hn, and this convolution, because we are talking about discrete systems and discrete inputs, this is discrete time convolution, not continuous time convolution. The formula for discrete convolution is k equals minus infinity to infinity, x of k, h of n minus k, or as we discussed earlier, you could change which part is fixed and which part gets flipped. So it could be h of k and x of n minus k too. Now there could be two approaches to solving this problem. One is for people who are more graphically inclined. What you could do is you could plot hn. All hn is it has a 1 at n equal to 2 and it is 0 everywhere else. And you can plot xn. What is xn? It is a delta at n equal to 1 minus 1, a delta of height 2, 0, and then it is a delta of height minus 3 for n equal to 1. So one way of doing this is you could use the flip and slide rule and you could compute yn in that case. The other approach can be that you directly plug in the values of hn and xn in here and compute it from there. Now, even though the summation may look daunting, actually that is perhaps the easiest way to solve this problem. I will write y of n equals summation k equals to minus infinity to infinity. I'll replace h of k with its value, which is since h of n is delta of n minus 2, h of k is delta of k minus 2. And I'll replace x of n minus k with its value. So x of n is 2 delta n plus 1 minus 3 delta n minus 1. So I write that with n replaced by n minus k. So I get 2 delta of n minus k plus 1 minus 3 delta of n minus k minus 1. Now this is an infinite summation, but this summation, each of the terms is getting multiplied by delta k minus 2. So again, you have to remind yourselves of the definition of delta function. So delta function is non-zero only when its argument is 0. Otherwise, it is itself 0. This means that delta of k minus 2 is equal to 0 except when k minus 2 equal to 0, which implies that k equal to 2. So for k equal to 2, delta of k minus 2 equal to 1 for k equal to 2. So this means that this summation, all the terms in this summation are 0 except for k equal to 2. That's the only term that will survive. So when we do that, we get y of n equal to, now I'll replace k, delta of k minus 2 by 1 times, and that is when k equals to 2. So I'll replace k by 2. So I get delta of n minus 2 plus 1 minus 3 delta of n minus 2 minus 1. And that is equal to 2 of delta of n minus 1 minus 3 of delta of n minus 3. Okay. So this is the answer that you get if you follow the explicit convolution formula. You can use the flip and slide rule also for this. In that case, for example, I could say I will fix my, so let's write the indices here. I'll go from, let's say, minus 3, minus 2, minus 1, 0, 1, 2, 3. These are my indices. I'll write k here. So I'm going to use this version of the convolution formula where I am fixing x, and I'm going to first flip h and then slide it. Okay. So what is x of k? Under this, I'll just write down the values. Let's do this division. So x is 2 for n equal to minus 1, and minus 3 for n equal to 1, and it's 0 everywhere else. Okay. And this goes on. And then I write h of minus k. So remember, h of minus k is just a flipped version. So h of k had a delta, had a value 1 at n equal to 2. So we get a delta at n equal to 1 minus 2 now, or k equal to minus 2 now. So this is h of minus k, and 0 everywhere else. Okay. And now we can ask ourselves, what happens when I slide this thing? Okay. So if you look at y, or for example, if you want to compute y of n for n less than 0, you can see that you have to, that means that you will be sliding this h of minus k left. And if you keep on sliding this to the left, it is always going to be multiplied with 0. So all of this will be multiplied with 0, 2 times 0, 0, 0. And the summation will always be 0. Right? So you don't have to compute all the slidings to the left. You can simply say that yn is equal to 0 for all n smaller than 0. What about for yn equal to 0? Yn, what about the case of yn for n equal to 0? Well, that is just multiplication of this, right? So when I multiply these two sequences and I add the values up, I get y of 0. Well, if I do that, all of the multiplications will be 0, and I add them up, I get 0. So y0 equal to 0, or yn is equal to 0 for n equal to 0. I can now slide it 1 to the right, so I can have h of 1 minus k, which will give me the value of y1. So if I do that, I get 0, 0, 1, 0, 0, 0, 0. So if I multiply now, I get 0 times 0 is 0, 0, 0. 2 times 1, I get 2 here. Minus 3 times 0, I get 0. And everything else is 0. So y1 comes out to be 2. I can now slide it further to the right. I can write h of 2 minus k, in which I get 0, 0, 0. 1 gets shifted further to the right, 0, 0, 0. Now if I multiply 2, this is the only non-zero. 2 is getting multiplied by 0, I get 0. 1 is multiplied by 0, I get 0. Minus 3 is getting multiplied by 0, I get 0. Effectively, y of 2 is 0. I can compute y of 3 minus k, which will require shifting it further to the right. So 0, 0, 0, 1, 0, 0. Again, all the terms will be 0 except this term will be minus 3, and I add them all up. I get y of 3 equal to minus 3. Now, I could try asking what happens after y of n for n bigger than 3, but you can see that if I slide this any further to the right, the only non-zero in this h of n minus k is now farthest to the right, that it will never get multiplied with a non-zero. So we know that for all n greater than 3, actually y of n will be equal to 0. So what do we get? We get that y of n is 0 for all values except at n equal to 1, its value is 2, and then at n equal to 3, its value is minus 3. And that effectively is written as 2 of delta n minus 1 minus 3 of delta n minus 3. Now, many of the students also noted some interesting things from this and were able to give the answer rather quickly. Some students were able to remember that when you are convolving with a delta, all that happens to the input is it gets shifted by the amount. So since the delta is at delta n minus 2, this whole function gets shifted to the right by the amount of 2, and they were able to quickly give the answer this. So this is our input, and the only thing that the system is doing is it's shifting it to the right by 2. Okay. As you can see in this plot, this is exactly what you are getting. Other people were able to use the superposition principle, which we will also talk about in part 2. So part B of this question now asks you to give the output to this input, but without using the convolution formula, and instead just using the superposition principle. So if you want to use the superposition principle, what you are required to do is divide this input into pieces whose output you know. Okay, so let's look at that. We'll just write down the input. So as a reminder, hn was delta of n minus 2, and our xn that we are told is 2 times delta of n plus 1 plus 5 of delta n minus 3 of delta n minus 1. So if you look at it, this plus this part is what is given in part A of this question. So I can write this as 2 of delta of n plus 1 minus 3 of delta of n minus 1 plus 5 delta of n. Okay. Let's call this input as x1n and call this input as x2n. So we are asking what is the output when our input is sum of these two inputs. Because this is an LTI system, we know that the output yn will be equal to the output of the sum of these two inputs. So output of x1n plus output of x2n. Okay. Now, what is the output of x1n? As we said earlier, x1n is exactly what we have in part A, and we computed that output. So the output of x1n is simply what we computed earlier, which is 2 of delta n minus 1 minus 3 of delta n minus 3. Okay. And what is output of x2n? Now x2n, for that we have to directly look at, again, we are not going to use anything other than superposition. Let's look at this. What is the definition of impulse response? The definition of impulse response is whatever is the output in response to an impulse. So this is an impulse. So actually we know by the definition of impulse response that when we input delta n, we get back h of n. Now if I input 5 delta n, what do I get back as output? I better get 5hn because it is a linear system. It's both linear and time invariant. This is the linearity property. So the output of 5 delta n is simply 5hn. So my answer is, using the linearity property, simply delta of n minus 1 minus 3 delta of n minus 3 plus 5 times delta of n minus 2. Okay. So again, the main thing we used is that we wrote our input as a sum of two inputs whose output we know. We know this output because of part A. We know the output of x2n because the definition of an impulse response is what is the output when you input an impulse. So we were able to compute 5 delta n's output, which is simply 5 times the impulse response. I hope in the presence of this video and when you receive your prerequisite quiz, you will be able to strengthen the concepts where you made errors when you took the quiz, and hopefully you can practice them further so that these concepts can remain with you throughout the duration of this course.